Let's start by talking about machine learning. We will quote Tom Mitchell. According to him, a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P. If its performance at tasks in T as measured by P improves with experience. So what does it mean? We will have experience here and performance. So this is for a given task. We can easily visualize what Tom Mitchell is saying by drawing such kind of graph where the performance increases by experience. So when a machine learning model gets more experience by training, its performance also gets better and better. So when we make it specific for supervised learning, what is the task T? The task T is to learn a mapping F from inputs to outputs. What do we mean a mapping F? Say we have input X and we want the output Y. So what we're trying to learn is F, which is a function which maps X input to Y outputs. We call the inputs features or predictors, and we call the outputs label, target, or response. The training set is going to be input output pairs. So we have the data set here. We have xn, which is the input, and yn, which is the output. So the data set is going to look something like this. x1, y1 is one row, for example. Then we will have x2, y2. So for each inputs, we have the outputs provided in the dataset. So let's continue with classification. The output space of a classification problem is a set of labels known as classes, which are unordered and mutually exclusive. So the output space could be hot dog and not hot dog. It could be cancer or no cancer. So when representing our dataset, we can use design matrix for small datasets, which is rows for examples and columns for features. Let me draw some kind of table for you. So here we have the rows, which is the examples x1, x2, and x3, and for the features, height, weight, and number of legs. So we don't have the output label here, we just have the features. The entries could be, for example, in meters. The weight we can represent in kilograms. In this case, the classification output labels could be cat, dog, and bird. Our model is going to learn how to map the height, weight, and number of legs into the output label cat, dog, and bird. So in this case, we can assume that the highest weight could be for dogs, and of course the number of legs also matters because birds have 2 legs. All of that is going to be learned by the model without us specifying the rules. Here we start with exploratory data analysis because we have to cleanse the data. We have to know if there is any kind of noise in the data. For example, so for more number of legs, we're going to expect more weight, and for lower number of weight, I'll expect to have less weight. And then let's assume that there is a low number of legs in tree for a high amount of weight, because we can see that when we have less number of legs, we'll get generally a lower amount of weight. But this specific example does not align with that criteria or that understanding. So what we do is we do exploratory data analysis by visualizing data like this, and then we will figure out any noise or any outlier in our data. So we can drop any of those unwanted examples from our dataset. Our decision boundary is what is used by our classifier that is learning to divide the data into regions. So in this case, our decision boundary could be like this. That means in this direction or to the right of the decision boundary, we get cats or dogs, and then to the left, we'll find birds, assuming that birds have less number of legs. We can toggle what we have discussed so far. So what does a loss function measure? It measures the cost of a prediction error. So for example, let's say we have a new data that we want to use as a test for our model. Let's say this is supposed to be a bird. Okay, and the model says this is a cat instead. So we know that this is an error, but how do we measure it, or how do we tell the model how far it is from the truth? That is done by the loss function. So we'll get into the math part, but let's talk about what empirical loss is. So this is the average loss of the model across all training examples. Let's say for simplicity's sake, we will count the loss as ones and zeros. That is a 0-1 loss actually. And let's say we have 10 examples, and out of those, our model got 4 of them wrong. That means we have 4 out of 10 empirical risk. When we come to empirical loss minimization, this refers to finding the parameters of the model that minimize the average loss on the training set. Let's talk about generalization. This is the ultimate objective. Of course, we can minimize the empirical loss, meaning we are optimizing for the training set, but generally we want the model to be able to generalize for different kind of new examples. This is what the empirical risk is, which I have described as the average. We are dividing by the number of examples here, and we are summing all of the loss values. So in 0-1 loss, we basically counted the number of examples we got wrong, which is 4, and then we divide by 10, right? 4 out of 10. So in this case, we are using 0-1 loss. We also have other options to calculate our loss. We can of course use asymmetric loss, where the loss is calculated differently for different kind of errors. For example, suggesting a poisonous substance as edible could be punished more than suggesting an edible item is poisonous because of the risks that entails. And don't forget that this n is the number of examples in the training set. That is what defines the empirical loss. When we're working with such kind of machine learning models, we want to capture how uncertain the model is. So we, instead of predicting cat and dog with 100% certainty, we're going to predict probability distributions over the possible classes. So for example, we can say for cat, the model predicted 70%. Let me write this as percentage. And for dog, we have 20%, and for bird, we have 10%. So probably the model gave dog more probability because the input specifies 4 legs and birds usually have 2 legs. And for cat maybe has very high probability due to the weight being very little compared to dogs. So that is something that our model learns. But when we have examples around our decision boundary, for example, let's say our test example is around here. That means we are not quite sure whether it passes here or here. When we evaluate, the model is going to be uncertain compared to if we have a data set around an example around here. So for examples where we have values close to the decision boundary, we're going to get a very uncertain prediction. For example, we could have this. The model is not quite confident that the input represents a cat. So we have dog and cat very close in terms of probability. So when we generalize this, we are basically going to have as many classes as we need, and our model is going to predict the probability distributions. But the output of the model is rarely going to be probabilities at first. It's probably going to be logits, which are unnormalized log probabilities. So in this case, let's say here, instead of outputs in percentages or in probability distribution, we will have something like this. So in this case, the model will output anything from negative infinity to positive infinity. The more confident it is in one of the classes, the value is going to be higher. This could be any number like 1,000. We are not restricting the model to outputs from 0 to 1, and instead we are outputting the logits. But of course we need the probability distribution to be from 0 to 1 as any kind of valid probability, and we want everything to sum to 1. So then we use the softmax function. Okay, we use the softmax to turn the logits into probability distributions. Great. So how do we define the loss mathematically? Define it as the negative log of the true label's probability. So for example, in this case, the model gave a higher probability to cat. Let's say the true label is indeed cat. That means since our model has predicted in confidence, the loss will be less. But when we see this example and assuming the true label is cat again, the loss is going to be higher than this one, because here the confidence is higher. We are telling our model to be more confident with such kind of inputs that the label is cat. So what is negative log likelihood? We average the negative log probability on the entire training set, which is another way of saying empirical loss. Here we have the log probability as defined above, and then we are averaging it. We have the negative sign outside here. We're dividing by the number of examples to get the average. This is basically the empirical risk. Maximum likelihood estimation is determining best parameters to minimize this loss, the negative log likelihood. Once we found the best parameters that minimize the loss, we denote those parameters like this with MLE to show that this is the best parameters that minimize the negative log likelihood. When we come to logistic regression, this is a special case where the function that is learned by our machine learning model is basically an affine function. So in mathematics we call an affine function where we have a linear transformation and then a bias term added, and the parameters that are learned by our model are bias and weights. Here we are learning bias and the weights. This is a basic formula. Keep in mind that this is a very basic form of a classification model. So let's come to regression. When do we implement regression? We implement regression when we want to predict real valued quantities instead of a class label. Let's take a simple example where we have the width, height, as the input for the model, and the output should be area. This generally is basically a simple multiplication, so we expect our model to learn how to do multiplication in this case. So the output here is a real valued number, which means this can assume any value in the real number line. For those kind of problems, we want to use regression. How do we define the loss when we are trying to do regression? We most commonly use L2 loss, which is quadratic loss. The equation for this is as follows. We calculate the difference between the prediction of the model and the real value, and then we square it. So in this case, our area is 190. If the model had, let's say, predicted 180, the difference will be 10, and then we will square that to make 100. The mean squared error is basically the average on the training set. So for L2 loss, it's going to be as follows. The MSE is the average of the quadratic loss that we defined. The output of such kind of regression models is usually a Gaussian with the mean depending on the inputs to get the conditional probability distribution. So we have a Gaussian here. What we do here is we define it as a Gaussian where we are trying to predict y given x and theta, which is a parameter of the model. Here our model is basically learning this mapping function f, which receives x and the parameters. We are assuming the variance is fixed for this problem. When the variance is fixed, the MSE is proportional to the NLL, which means computing MLE reduces MSE. This is the equation that makes NLL and MSE proportional. We end up with a constant here, but if we assume that the variance is actually not fixed and it is actually learned, we're not going to end up with a constant, and will not be able to assume the NLL and the MSE are proportional. So the simple form of regression is for 1D data. Let me actually correct this. Yeah, so basically the simple linear regression has the following equation where we learn the bias, we learn the weight, and for any 1D input x, that can be a number 5. Okay, we just multiply with the weight, add some bias, and that's our output. But when we come to multiple linear regression, we can have multiple inputs the same way we have height, weight, and number of legs for our cat and dog example, but we will actually want to have a problem that is a regression problem instead of a classification problem. So for multiple linear regression, we have a single bias term, then we have different weights for each kind of input. Of course, this is a very simple model. Instead of actually trying to learn just the weights that linearly multiply the inputs, we can actually create a feature vector derived from the input and has a polynomial form. This is a linear function of the parameters, but it is a nonlinear function of the original inputs x. So let me show you what that means. We will use this feature vector, which looks as follows. So we have polynomial expansion here, where each input is going to be included in the formula, and we'll have more polynomial terms. So for example, if our feature vector included just this part, we'll have this kind of equation. If we had a cubic term, we'll have more weights and more terms here, like w5 x1 cubed and w6 x2 cubed. But doing this kind of manual feature extraction is not ideal. So that's when we use deep neural networks. In this case, we replace the feature vector by a stack of nested functions. We can just give our function this parameter v, which will pass to the feature vector, and this can become a recursive function like this, where each function L is a layer which gets its inputs from the previous layer. So here you can see this is f is capital L, which is the last layer, which gets its inputs from the previous layer, and goes back to the first layer that gets the input x. Now we will talk about overfitting. So overfitting is when our model fits the training data too closely. The problem is actually not the fact that our model is fitting the data very close to our training set. The problem is actually the fact that when our model also fits the irregularities in our dataset, it's going to miss the general idea or the general concept behind it. So for example, let's say we have data like this, where the true function or the true distribution that is generating the sample is actually something of a linear form like this. But our data sets are, let's say, like this, like a zigzag, and our model learns this curve instead. So now, because our model is too complex, instead of learning what it should have learned, which is linear, now it's made this kind of overly complex function. So if we had the true distribution here, and let's say there's a new example or new data x here, our true distribution maps here, maps the y value right here. But our model is going to predict around this complex curve. This difference is due to our model being too complex and fitting the dataset too closely instead of trying to understand the underlying distribution that generated our dataset. So we rewrite our empirical risk to make it explicit which dataset the loss is being evaluated on, which is the D train or the dataset train. So initially we had 1 over n, the total number of examples. Now we will have the length of our dataset that we're using for training. This is crucial because we will divide our dataset into different partitions, where some of it will be used for training and we will use other partitions for different purposes. Let's talk about the population risk or the theoretical expected loss. When we say empirical risk versus population risk, if we are evaluating the loss for our training set, we are talking about empirical risk. But if we had the theoretical underlying distribution that we don't have, then that is our population risk, which we could have got if we had every possible data item in our dataset. That we will call P star. So the population risk in this case, we will denote it like this. So the generalization gap is the difference in the two losses, the empirical risk and the population risk. When we have a big generalization gap, we can say that our model is overfitting. In simple terms, let's say on our dataset we are getting very low amount of loss because our model understands our dataset, but when it sees unexpected values which are from the true distribution, we get a higher amount of loss. That means the gap between how our model reacts to the data it knows versus how it reacts to unseen data is our generalization gap. But the problem is we don't have the unknown distribution, so we cannot get the population risk. That's why we will use a test set to approximate the population risk using the test risk. Okay, that we do by partitioning the dataset. So earlier here we made it explicit that we're using D train, which is the partition for training. Then we will have a partition for test, and we will do the loss on that. We're going to see how different our model is for unseen data. The third point I want to mention here is that we don't usually stop at two partitions for training and testing. We add a third partition, the validation set, for model selection. In the future videos we will see how different kind of use cases can be solved with potentially different kind of algorithms, different kind of models. Even when choosing a specific algorithm or a specific approach to our problem, we can choose different kind of hyperparameters, which can also make a difference